Welcome.
Thank you very much.
Yes. Professor Patricia Schady from the University of Bath, senior lecturer at the Department of Physics. If you're interested in physics now as sort of in your sixth form, and you click on all the sort of where should I go to, and you find one on YouTube, you may well hear Patricia's voice encouraging you to come, wooing you towards the Department of Physics, as I discovered when I was hunting around. But you've spent a lot of time actually in your career over in Germany, I understand.
I did, yeah, 9 years in total. Yeah.
So you did was it a postdoc over there, and then
I clung on for a while. So I was like 1 year and another year and another year, and then I got kind of a 5-year grant with my own group, so that was great. But the permanent position wasn't there for me, so I'm very happy to have come to Bath. But that was what brought me here.
Oh, yeah. Well, it's wonderful to have you. Thank you very much for coming down the hill to see us and to talk to us all about gamma ray bursts.
Thank you very much. Yeah.
Just for your understanding, there is a camera just here.
I'll stand there.
If you wanted to be in full view, this is the place to be.
I will place myself here. Okay, well, thank you very much for the invite. It's very nice to be here. I should say this is my first time of giving a talk to Bath astronomers. So I don't know whether I've pitched it right. We shall see. I think you're quite an intimidating crowd, to be honest. I think there's loads of stuff that you know that I don't know, but let's see how the questioning goes. But because of that, do please tell me, you know, I guess this is informal. So if something's kind of not, if you're not following something, just ask questions in between, that'd be great. So yes, I'm going to be summarizing kind of what I've been doing for most of my research career, which is using gamma ray bursts to trace the universe, in particular the high redshift universe, and specifically looking at the chemical composition of very distant galaxies. So this is a problem. I'll be going back and forth a little bit. Okay, so we start here a little bit. Why do we care about what I'm studying anyway? And so I think this is very nicely depicted in this picture, which might be a picture that you've seen before. So here we have a little representation of the evolution and the formation of the universe from the Big Bang. And then you have quantum fluctuations that then grow to produce larger and larger fluctuations that then allowed the conditions to be set in order for baryons to be able to collapse and form the first stars and the first galaxies. And we want to understand that from an observational perspective. We want to have more evidence of exactly how this picture grew. This is very much, we've got pieces of this picture, but we want to be able to really be able, piece this together through our observations. Now, much of the information that we have currently from the furthest distances, so from the cosmic microwave background, come from Planck, but now through different methods, we're able to really push back in terms of what we're seeing and being able to probe this picture through for a long time now, for a couple of decades with the Hubble Space Telescope, but of course now very exciting times with James Webb Space Telescope, which is just, I'm sure you've been following it. It's absolutely breathtaking, the data that's coming out of there. And so I just want to go through a little bit what we can do in terms of going further back in time, how our telescopes and observatories are performing in terms of being able to actually get information. So to just have a cartoon on the information that I'm particularly interested in, here, this is a representation of the baryon cycle, as it's called. So we have the formation of stars and the formation of galaxies, and this is due to gas and baryons falling into the gravitational potential well. But it's a complex cycle that's taking place to produce the galaxies that we see today. And so in this picture, I start up here with the gas cooling. So we have pristine gas, we call it. So material that's not been chemically enriched yet. This is falling down into these gravitational potential wells. It's condensing, it's cooling, it's allowing the first stars to form. The stars are then, it's forming molecular clouds from which stars can then form. And then as the stars evolve, the most massive stars turn into supernovae, and then they enrich the material around, which in turn then cools to form the next generation of stars. And so this is the enrichment that we've got going on over time. And then to add to this complexity, we have outflows as well. So as material is ejected by the supernovae or by supermassive black holes in the center of the galaxies potentially, then the material is mixed in around. And so we'd really like to understand this picture much better. What are the dominating factors? How dominating is this pristine gas that's falling onto the galaxy? How efficient are the stars or supernovae actually ejecting their material out of their galaxy, or does it just float and then rain down again onto the galaxy? These are all kind of pieces we want to know. So looking back at this picture, ways in which we can study how this baryon cycle is kind of forming and evolving is by looking at the chemical composition of different galaxies at different look back times. Now, if we look today at our galaxies, we have beautiful galaxies such as this one. We can take spectra, so this is gas that's been ionized by the stars, and using these emission lines, we have diagnostics that can give us an indication of what the chemical composition is. So that's nice. However, if we then go further back, oh, sorry, yes, I forgot about this slide. Okay, so what we can do with this is we can build a picture of, for example, this is one of the ways in which we can look at galaxy evolution. We can look at lots of galaxies of different masses here on the x-axis, and we can determine their chemical composition by using spectra like the one that I showed. And we can see things like this so-called mass metallicity relation. So we have mass on the x-axis, and on the y-axis we have the chemical enrichment, which is increasing going up. And so we find that as galaxies become more massive, they also become more chemically enriched. And then we have a plateauing going on. And we think this has something to do with the outflows and inflows and what's the dominant kind of piece of this jigsaw here. Yes.
Can you give us a quick recap on metallicity?
Oh, sorry. Yes, good when you call me up on that. So in astro language, metallicity is going to be, a metal is any element that's heavier than hydrogen or helium. And metallicity is going to be the fraction of these metals, so-called metals in mass, over the fraction of over the mass in hydrogen. And we care about metallicity because metals come from stars predominantly. And so by tracing metallicity, we're really tracing star formation rate is what we're doing. And so that's why we're interested in this. So in that sense, this picture makes a lot of sense. As stars are being created, being formed, the stellar mass of that galaxy is increasing, but in turn, those stars are enriching their environment. And that's what we're seeing over here. So this is a very useful, picture here that we have. We learn a lot about how galaxies evolve. But now let's see what's happening if we look further back. So our galaxies, we've still got lovely images here from the Hubble Space Telescope, but our spectra now, they're a little bit noisier. And importantly, we're losing some lines. So now the lines, they're being redshifted out, right? So they're now over here, and our spectrograph no longer catches them. So it becomes a little bit difficult. We have to use different tools now to get a chemical composition, which is now a different kettle of fish, because now we're using different diagnostics to trace this metallicity. But nevertheless, we can do this, and people have tried to do this. So pushing out to here, redshift 2.26, this is about the universe is about half its current age. And what we have is we have this same relationship between mass and metallicity, but at different look back times. So this is today, and then going further back in time, we have going down from yellow, black, this cyan to red. And so what we're finding is that galaxies that were of the same mass in the more distant universe were less chemically enriched. So this again is feeding into this picture of how galaxies are actually building their mass and at what rate and what speed, and what's the role of inflows and outflows. But now we're really pushing the frontier. We want to go further than this, is one thing we want to do. But if we're trying to go further with this, pre-JWST, this is really state of the art. We had our Hubble Space Telescope, and you can see that when we start pushing really to the early years of the universe, we have these red blobs. We no longer have these beautiful detailed images. And importantly, we just don't have the spectra that we need to be able to determine what the chemical composition is. Now, of course, this has changed somewhat with JWST. So I'm sure you're all very familiar with this picture now. Beautiful images. But what got me incredibly excited is that these little red blobs, which are seen in so much more detail in these images, JWST is actually providing us with spectra, which is illustrated over here, and it's just showing how these same set of lines are shifting out to further and further wavelengths, larger wavelengths, showing the distance of the galaxy. This is the more distant galaxy down here. But what is key about this, HST was also able to get some spectra, but what's key here is that JWST is actually giving us lots of lines. So this one, when it came out, I mean, I was kind of geekily excited about this particular spectrum, because this galaxy is 13.1 billion years away, right? And And the lines, I mean, not only that they detect all of these lines, this particular line, this oxygen line next to the hydrogen, this H gamma, this is a very weak line. This is the gold standard. This is what we want to detect to be able to determine metallicities. I'm not going to go into the technicalities of that, but it's just to illustrate the sensitivity. It turns out actually that this line is stronger in galaxies at 13.1 billion years than it is at galaxies in 7 billion years, which are the galaxies that I'm looking at. But nevertheless, we have lots and lots of spectra. So lots of wonderful science is going to be coming out of this. But, so there has to be a but, otherwise what's the point of my research, of course? First of all, okay, we have lines, and JWST is going to give us lots of lines. How do we equate these lines into a metallicity? Okay, so what's the diagnostic that we're using? There are lots of different methods that have been proposed, each with their advantage and disadvantage. Here I'm just giving you a snapshot of the current issues that exist with our metallicity diagnostics, we call them. So we have, once again, this stellar mass down here, so the mass metallicity relation. And what I just want you to take away from this image is the fact that each of these colored curves shown on this plot corresponds to a different diagnostic that has been used, a different method to translate emission lines to a metallicity. And you can see that there's a lot of differences. Now, they all show a similar kind of shape, but really there are differences in this shape, whether it turns over, how quickly it flattens out, how high it is. This does really matter. So we have problems at redshift 0. So any of the diagnostics that we used here at further redshifts are going to have even greater uncertainties because we don't know what the conditions were like in those galaxies. So that's a little bit problem one. JWST is going to do a lot to address this problem. But then we have another issue or point that's worth highlighting, which is I've been talking about emission line spectra. Emission line spectra is the gas that's excited by stars. That means that when we get metallicities from these kind of data, we are really only probing one bit of what we would call a galaxy, and that's the star-forming regions within a galaxy. So in a galaxy, we might have like a disk, we have star-forming regions within, but I've already mentioned we've got accretion of pristine gas falling into that galaxy. We've got outflows of material being extracted from the galaxy. Maybe this rains down again. And so only a small portion of the metals produced in this galaxy are actually represented by what we see here. And so that's really what I'm interested in doing, is in trying to piece together more information in terms of this picture to see how the metals within these regions that we trace with our emission line spectra actually relate to other portions of the galaxy. So this is where I argue that gamma ray bursts come in, and they can be incredibly effective probes, which are complementary to the emission line data that we have. So I don't know whether gamma ray bursts is something that you've heard of or you've had a talk on, or something that just, okay, excellent. Right, so gamma ray bursts, they're very much what they say on the tin. So they're an enormous explosion of gamma rays. They were discovered in the late 1960s. It's quite a nice story. So it was during the Cold War. There were the USA sent out these Vela satellites in order to be able to detect any nuclear activity that was taking place down on Earth, and they didn't detect any. Instead, they detected nuclear activity that was taking place beyond. For a very long time, there was a long discussion on what these things were. The energies coming from these outbursts of gamma rays, of very high energy radiation, was enormous, and they couldn't understand what it was. Many scientists wanted to put gamma ray bursts into our galaxy, because if they were any further away, then the implied energetics would be even greater. But this picture over here, this was taken from the Space Telescope. This is in the 1980s, no, 1990s, early 1990s, really indicated these things were extraterrestrial. So if they were from the Milky Way, they would line up with the plane you would expect. So these things, like, even more energetic than it was initially thought. And this is just an image of that's been put together of a particular gamma ray burst. So they come in two forms. They come in either short bursts or long bursts. Short bursts, we're talking about less than 2 seconds. If you look at the duration of gamma ray bursts, you see this kind of bimodal distribution. And so we've just put a line there. We've got short bursts, less than 2 seconds, long bursts, which lasts for tens, hundreds, maybe thousands of seconds in this gamma ray energy emission. And so the radiation that comes out from these outbursts is at that time the brightest gamma ray source in the sky, so more luminous than the entire Milky Way, for example. So here I just wanted to put a little scale to kind of put it all into context. So how do gamma ray bursts compare to other things that we might be more familiar with? So we've got the lightning bolt, 10 to the 10 joules, hydrogen bomb, 10 to the 16. We've got a supernova, 10 to the 44 joules or so. And then we've got the most luminous GRB, so we're about 10 to the 47. So these are, from the physics perspective, trying to understand and comprehend how it's possible to produce so much energy in such a short space of time is a real challenge. So the mechanisms or the progenitors are fairly well understood. The details aren't, but our understanding is that regardless of whether we're talking about short gamma ray bursts or long gamma ray bursts, we have the formation of a black hole, of a stellar-sized black hole. Material accretes onto that black hole, and that somehow launches these relativistic jets. And so that's the key. The emission is, the material here is moving it close to the speed of light. And so that's giving it this Doppler boost, which is the cause of the huge energies we're seeing. And so we initially see the gamma rays, which we believe is happening within the ejector as the material is moving out. They've got shells of material plowing together, forming gamma rays. And then later on, we do see the gamma ray bursts at longer wavelengths. So this is called the afterglow, where we see it in the visible X-rays radio. And this is the bit that I look at. This emission lasts for much longer. Now, in terms of the two different kinds, we've got short GRBs, which we believe come from the compact mergers of two neutron stars, or a neutron star and a black hole. So these have also received a lot of attention with gravitational waves now, because of the detection of gravitational waves and a neutron star binary merger and the GRB. This is possibly what David Sang will be talking to you about. I'm more interested in this one. So the long gamma ray bursts are the collapse of a massive star. So similar to a supernova. A supernova is accompanies a long gamma ray burst, but it's a special kind of star that produces a supernova that can also produce a gamma ray burst. And so the reason I'm very interested in these is because these are more luminous. We can see them out to further distances, and they trace star forming regions, and they trace, star forming galaxies, which is what I'm interested in. So a few kind of advantages to highlight about gamma ray bursts, or why I'm interested in them. So this is just an image to show that the gamma ray burst has gone on over here. Here's a zoom in. You can see that when this is the afterglow actually now, this is an optical image. So the optical emission is larger than all the stars in this galaxy. We don't see this galaxy, or there are examples of galaxies that we don't see before that single star has exploded. And when that single star explodes, we then know that there's a star-forming galaxy there. And we've seen these things. Once we were a record breaker. This is now out of date. But once upon a time, here we have a GRB, and that GRB was detected before this galaxy. Now JWST, we haven't got a hope, but there was once upon a time, GRBs were record breakers. So they peak at around redshift 2. So this is when the universe was about half its current age. So that's another benefit. I'm interested in that epoch of the universe. But then also, this is just to show the evidence that we had of the fact that gamma ray bursts, long gamma ray bursts, really do trace massive stars. So what we have over here, by the way, GRBs are named after the date that they occurred. So this one occurred on the 29th of March, 2003. And what we have is, initially we have a spectrum of the GRB. The emission from a GRB is non-thermal. This means it's just a simple power law. It's a featureless, simple power law like this. The features that you see here are things from our atmosphere, for example. So it's just a power law like this. But then you see with time, each of these colors is the same target, but the spectrum is evolving. So with time, the shape is changing until eventually this thing really looks like a core collapse supernova. And so this was the kind of evidence indicating that gamma ray bursts are the death of a massive star, because we know that core collapse supernova are the death of a massive star. And then this picture, I think, is key to the science that I do. So I've already mentioned that gamma ray bursts, long gamma ray bursts, they have this simple emission lines, power law spectrum. And so this is an example of one such optical afterglow spectrum, which happened at redshift greater than 2. And what we see here is you've got some attenuation due to dust or whatever it might be, but this really is just a simple power law. which means that any material that's been eaten away, or any light, sorry, that's been eaten away by material between the gamma ray burst and us, can actually be seen very clearly, and we can measure how much material was needed to produce these features. So this big one, this is the really important one, that's hydrogen. So that's neutral hydrogen at the location, at the host galaxy of the gamma ray burst. And then we have lots of different metal lines. Some of these are due to metals in our galaxy, in the Milky Way, but we know which ones those are. Lots of these are due to metals in that gamma ray burst's host galaxy. So we have the ingredients we need. We know how many metals there are of a particular, well, we know a certain element, how much silicon-4 there was, for example, in the host galaxy. We know how much hydrogen there was. We can use that to determine the metallicity in these very distant galaxies that otherwise we would not know are there because they're small and faint. So now with gamma ray burst, if we go back to kind of this picture that I had before, we now are probing something that's here. So what we have is gamma ray bursts are tracing stars. So the material that is absorbing the light from the gamma ray burst is somewhere embedded where the stars are. But we know these elements, this is neutral hydrogen. We know the material is neutral. It's not the ionized stuff that's inside these star-forming regions. It's the stuff between the star-forming regions. So we, with these measurements, can measure what the metallicity is within here. Now, this is important because this tells us something about how well the material that's falling into the galaxy mixes with the material that then is enriched by the stars. So that gives a little bit of information there. There are other similar probes to the metallicity of this picture over here using what are called QSO DLAs. So what we have here is a picture of a background, a very luminous background source, which is a quasar. So this is a supermassive black hole that's producing a huge amount of energy. That light from that quasar travels to us in a similar way to GRBs, but what's different here is that it's not the host galaxy of the quasar now that produces the absorption. It's intervening systems. It kind of travels through the universe. If it passes through the line of sight, crosses a galaxy, then it produces this hydrogen absorption that we see here and lots of other metal lines. This is just material in between. And so this has been used for a very long time to study the kind of metallicity of galaxies. But what we're probing here is we're no longer in the disk of the galaxy. We're further away. Okay, because this is just an intervening system. So I've got a better example here. I know that comes later. Okay, I'll show you an example shortly of where the difference is in the kind of offset, if you like, of what we're probing with our QSO DLAs. This is just a picture of what you can do then if you have these observations, right? If we have lots of metallicity observations using GRB DLAs, they're called. DLAs refer to this immense reservoir of neutral gas that we see with those big absorption troughs. We only see this if for GRBs, we only see it if it's a redshift greater than 2. But what this plot shows is the gray data points are metallicities that we've measured from absorption in QSO DLAs, and the colored points are from GRBs. And so really what I want to emphasize with this plot is that we're pushing right out to redshift 6.5. So, you know, this is when the universe was 800, I think you're probably better than me than that, actually, 800 million years old or something like that. So we're really pushing far, and we're pushing much further pre-JWST than we were with emission line spectra, which were more like here. I think I've kind of indicated. So pre-JWST, this is kind of where we are in terms of how far in redshift space we're probing the cosmic chemical evolution, if you like. Key points are that emission line metallicities are not going so far out in redshift. Another second point is that there is a systematic offset in the metallicities that we measure from emission lines to what we measure with absorption lines. And so this is the key. Why is that? Is it because our emission line diagnostics are wrong? Is it because neutral gas, which is what the data points are representing, has a different metallicity to the star-forming gas, which tells us something about the gas accretion? So this is what we want to investigate further. Now, a point about the differences between GRBs and QSOs no, I still don't have that picture. I'm just going to go to it because I've been meaning to talk about this for ages, is represented with these two figures. So here we have a mosaic of GRB host galaxies. And you see the GRB, you see the location of where the GRB was. In some of the images, we still see the gamma ray burst. In some, it's gone. So these are all, yeah, HST images. But the point is, you can see that the gamma ray burst really happens very central to the galaxy itself. These are nearby GRBs. This is an example of a QSO DLA. This is the very luminous QSO, right? This is the, yeah. And as that light travels through, some galaxy, and when they did this paper, they thought it was any of these galaxies is the one that's causing the absorption. And in the end, they realized it was this G1 galaxy. This was the one that was producing absorption lines. So this quasar was probing the metallicity of this galaxy. But you can just see the offset, right? This QSO is not probing the material that's in the center of the galaxy. And so I think, you know, that has, it's complementary, but that is, one could consider that as a disadvantage in terms of, you know, we're interested in the material closer in, but I'll touch on that again shortly. So if I just go back quickly, in terms of QSO DLAs, people have been looking for a long time at trying to understand the differences in the chemical composition of the stuff in star forming regions and the stuff further out. And so here's kind of a cartoon of it, but in terms of the data, we have over here on the y-axis, the metallicity that's been measured from the emission lines. So that's from these kind of star forming regions. And down here, we have the metallicity that's been measured from absorption in the QSO DLA. So probing the neutral material over here. And this line is the line of equality. So we see that there's an offset in the metallicity. Why is that offset there? Is it because the neutral gas is fundamentally less enriched than the ionized gas? Or is it actually because of the kind of the difference in spatial, you know, the spatial offset in the region that we're probing, because galaxies are more enriched in the centers than they are in the outskirts? We can't answer that question with QSO DLAs, but we can answer that question with GRBs because the GRB probes the center. So I think that's kind of the selling point for GRBs. Okay, so this is what I want to do. I want to look at GRBs. I want to get their emission line data of their host galaxies to probe this bit. I want to get their absorption line metallicities from the gamma ray burst itself that probes that bit for the same galaxies. So what I did was I already had this information for a sample of GRBs, but then I wanted to get these data from JWST. JWST was the only, is the only observatory that can do this, because these galaxies are too far and too small to be done in any other way, including HST, within a reasonable amount of time anyway. So the JWST program was kind of modest. So it's just to observe 10 GRB host galaxies. They are indicated here with these circles. So these galaxies were selected to be galaxies where the absorption metallicity was very accurate, where we had some kind of emission detection. The galaxy was detected in emission, be it in spectra, be it in imaging. Otherwise, I don't think you can convince anybody to stare at a blank patch of sky until you get an emission line spectra. And that we could get a decent signal to noise within a reasonable amount of time. And so this left us with just 10, but we want to continue this project. And so we've got the redshifts kind of ranges between 2.1 and 4.7. So this region over here. So much further than what we have with emission lines. And then the metallicities that we're probing from absorption is from 0.2 solar. So that's very unenriched to very enriched. So we've got quite a large range there. And we want to fill in this picture now, but with our gamma ray burst observations. Now, what we have on this picture is there's one data point, which is a single gamma ray burst that thus far we have been able, pre-JWST, to get an absorption metallicity, so the metallicity of the neutral gas, and an emission line spectrum, which gives us the metallicity of the star forming regions. And we've been able to plonk it on there, and it kind of tallies with our QSO DLAs. These data points down here are my JWST targets, where we have this metallicity from the absorption, but I want JWST to tell me what this metallicity is. So far, I just know it's somewhere along this line. So the first results came in, I think this was about 3 weeks ago or something. And the gamma ray burst host galaxy was this little smudge over here. You have no idea how nervous I am every single time I get an email saying JWST is going to observe your next target, because I'm all about macro astro. I do gamma ray bursts, the most luminous things ever. Twiddle, it doesn't matter if I because it's so big, I'm always going to detect it. But now the precision that's needed in terms of getting my slit in the correct place. So we get the position of the bright star, and then we tell the JWST what's the distance between that bright star and here, and then stick your slit over there, which is a tiny, tiny, tiny little slit. So the possibility of missing and actually pointing that, getting that slit on a patch of sky, I'm just terrified every single time. So I'm 2 down, 8 to go. But this was one of the better ones in terms of the imaging data that we had pre-JWST wasn't bad. So we could fairly accurately know where that slit was going. The data are preliminary. These are all very new. So what we have over here is, this is the second data point. So this is using JWST. What I show here is this is the 2D spectrum. So this is the white dots correspond to the peaks of the emission line. Okay, so we have no continuum, we have nothing here, but then the fact that we have a dot here, that just tells us there's emission there, and it's a line, it's not continuum. So this is oxygen 2, this is oxygen 3, this is H alpha. So still quite ugly for now because I need to do optimal reduction. These are just the data that I was able to download automatically, so kind of the automated, fairly noisy spectra, noisier than we hoped. We're hoping to be able to improve that with more reduction, but clearly the oxygen 2 is detected here. So that is unambiguous. It's about shrinking those uncertainties to be able to kind of shrink those uncertainties that you see over here. Nevertheless, we've got a second data point that's lying relatively, it's lying a little bit closer to this line. And then very much hot on the press, off the press, yesterday morning, I received an email to tell me that my second observation was in. So this one is not a single slit. This is not a fixed slit observation. I have 2 targets which had evidence of being extended. And so what I did was I requested that we observe it with IFU. And so I just want to describe what that is. Here is a picture of what an IFU is. An IFU is, if you have an image of a nebula or whatever it might be, every single pixel on that image is a spectrum. So it's a cube. So if you do a cut, you can get an image of the same galaxy at a different wavelength. And so here we have the HSD data, which showed, this is the gamma ray burst itself, that's the afterglow. And previous analysis showed that this thing over here and this thing over there was at the same distance as the gamma ray burst. And so that would indicate that these 2 things, which are very, very far apart, they're 8 kiloparsecs apart, that they're somehow interacting. And the gamma ray burst has come out of some star formation that's happened here. And so this is the field of view. This is where I plonked the IFU. So it's much bigger now, right? So it's much safer. It's not the scary thing with the slit. And these are the data, again, preliminary. I haven't done anything to them. I just downloaded, but I'll kind of guide you what you're seeing here. So this has got to do with the dither. This has got to do with the observations. They observe here and then they observe here. It's got to do with background subtraction. The point being, these splodges correspond to these splodges. So the difference is, this is imaging, this is spectra. JWST, you've seen now, is able to produce much more beautiful high resolution images than HST, but these are spectra. And so if I stick my pixel on my cursor, this is some software on my computer, if I stick my cursor somewhere, I think I stuck it somewhere over here. Down here, you get the spectrum. So that's this bit. And if I move my cursor around, this thing changes because it's showing me a different spectrum. And so when I put my cursor on there, this came up, which is clear. So there's no continuum. Again, this is all 0, but the emission lines pop up. And over here, we have again this bright oxygen 3 doublet. And that's what I was looking for. And sure enough, these 2 things are exactly the same redshift. And so we've got 3 complexes. We've got this thing, which is here. We've got that thing, which is there. And then over here is whatever was underneath the gamma ray burst that we can't see in this HST image. So I've done some preliminary analysis to be able to get a metallicity of sorts. We've got, how do you convert your emission lines to a metallicity? But that's a different talk. And so this one, preliminary, it's over here. These are just preliminary data. Signal to noise is very nice on these data. Almost, I wonder whether I've done something wrong. Apparently there are no uncertainties, which is clearly not right. But anyway, we clearly detect these lines. And so, yeah, the picture is kind of being populated. As more data come in, questions I want to ask are, first of all, what is the typical offset between where my red data points are lying and where this line of equality is lying? So that's answering the question, what is the average difference between the metallicity in the neutral material within the disk of the galaxy and the metallicity that's been enriched in these star-forming regions? And the reason I care about this is because this is going to tell me something about how efficient the metals produced here are being ejected and mixed around versus how efficient is pristine gas coming in and fueling further star formation. It's kind of that direction. A second question is, so how does this red bar that I've kind of indicated here, which corresponds to the difference here, compare to the difference when we look at QSO DLAs? So this kind of blue line that I've tried to show, I mean, you know, this is obviously just drawing, but really I want to understand how does this metallicity of this material, which is neutral, compare to the metallicity of this material, which is neutral? Is it the same material? Is there evidence to indicate that they're quite comparable and it's just falling in? We would get an indication of that if the offset were comparable. And so this is kind of the piece of the jigsaw that I'm trying to put together to build up how metals are distributed within their galaxies. And then this one, I think, is quite controversial within the galaxy community, but not at all within the GRB community. So GRB scientists argue that getting a metallicity from these kind of data are more reliable than getting a metallicity from these kind of data. These kind of data, we have our hydrogen, we have our metals, we had to do some corrections, but by and large, it's model independent. We measure how many metals were needed to produce that line, we measure how much hydrogen was needed to produce that line, and then one over the other gives us the metallicity. Bish, bash, bosh. Here, there's an awful lot of assumptions that have to be made in order to turn these line ratios into a metallicity, related to how much material you're not seeing because it's not being emitted in oxygen 3 or in oxygen 2, it's being emitted to something else that we're not seeing, or all sorts of kind of differences that may arise in terms of how an excited cloud of gas, what kind of spectrum it produces. You need to kind of equate what properties of that excited cloud will then produce this emission spectrum that we see. So within the GRB community, there are some that argue that we can use these kind of data to calibrate our emission line diagnostics in the distant universe. So we can look at this metallicity, look at that metallicity, and then say, okay, this bunch of lines and line ratios correspond to that metallicity. And that's. But the galaxy community don't like that at all. And it's fair enough. I think we're both wrong, actually. This is only a single line of sight. We get one depiction of a galaxy through that line of sight. Maybe if the GRB had happened over here, the metallicity we'd measure would be slightly different. These kind of data don't suffer from that. But I think it will be interesting to compare one to the other, if nothing more, to be able to see whether we can find a relation that tells us if we measure the absorption metallicity, can we then guesstimate what the metallicity of the star-forming regions in that galaxy are? Because if we can do that kind of thing, then maybe we can, you know, combine these bits of information. So we have different bits of very informative data here, which are very much looked by different communities and very, very infrequently combined. If we can actually know, at the moment, it's a little bit like apples and pears. These data a little bit can't be compared to those. But if we can bring together that connection, maybe we can start putting some of this on this plot and vice versa. And we can be using the advantages of absorption line metallicities to push out to higher redshift. But we can use the advantages of emission line metallicity where we have more information about the galaxy itself, such as its stellar mass and what have you. So that's a goal that would be nice. At the moment, I only have 10 targets, of course. The galaxy community has hundreds of thousands of targets. I always get data envy when I see any talks given by kind of emission line or imaging people. But I think this is a step in the right direction, and obviously the kind of the hope will be to be able to continue the JWST project with new cycles. And I think that brings me to my summary. So, you know, GRB host galaxies, they do offer a unique opportunity to investigate the relation between the ionized and the neutral gas within distant star-forming galaxies. Gamma ray bursts really do provide a very sensitive and unique probe of this neutral interstellar medium in these distant galaxies, which many times would otherwise not be seen, because gamma ray bursts generally arise in low mass small galaxies, which are not the ones that are usually seen in emission. Obviously, JWST is going to be revolutionary on many levels, but within GRB astronomy that also. So it's going to allow us to address some of these questions that I highlighted in those last 3 slides. And then my hope now, the new call has come out. And so the next deadline is towards the end of January. And I will definitely be submitting something to be able to continue this campaign of increasing my little poor sample of 10 to something a little bit more substantial. So that's it. Thank you very much. Apologies to those online, but I found that I was going back and forth to change slides. So, yeah.
What questions does everyone have? I was actually going to ask, because you seem to be GRB mad since day one. So what brought you into GRBs?
So I initially, when I applied for PhDs, I actually wanted to do quasars because they look very exciting. And I got offered a PhD in GRBs, and I enjoyed that very much. And I joined the GRB science in a very exciting time, because a new mission had just been launched called SWIFT, which was fairly revolutionary in terms of our understanding of gamma ray bursts. It was a mission dedicated to gamma ray bursts that could slew very quickly. So it would detect the gamma ray bursts and gamma rays, and then within a minute, and it also had on board, well, it's still up there, it also has on board an optical and X-ray camera. And so it could very quickly slew and be looking at the X-ray and optical emission within a minute. And so we were able to connect how that prompt emission, that gamma ray emission, linked to the afterglow emission. So that was very exciting. And so I've always, but I still, because of that quasar thing, I've always liked the distant universe. That's always been my thing. And so that's kind of naturally why I fell into GRBs as probes. Nevertheless, a little bit of data envy story. So the picture that I showed you of the IFU, so where you have these cubes, where you have an image and every picture, every pixel is a spectrum. If you look at a GRB, well, you saw my image, my JWST image of a distant galaxy. It's not these beautiful things with spiral arms. I wanted to play with beautiful things with spiral arms. And so I did kind of change my science area a little bit to be able to get my hands on some of those data, because the GRBs generally happen at very large distances. And so I moved a little bit more into supernovae, kind of related, and then I could move into more nearby galaxies. And then I got very interested in just metallicities, so looking at emission line diagnostics. So GRBs aside, not related. So my current PhD student is actually looking at metallicity diagnostics and that whole problem about them not agreeing. So I have kind of a little bit gone off and tried other things, but I think at the core, really, GRBs is I mean, I've been waiting for JWST for about 10 years. I knew this is what I wanted to do. So yeah, that's kind of, I don't know, I like it. Yeah.
So when we used to sigh that JWST got delayed again,
yes,
you were doing more than sigh.
Yeah. I mean, well, so there was the first call for science proposals happened. I remember this day so clearly. So the call happened when I was still in Germany for cycle 1 for applications to observe. And I got a little bit disorganized at that one. And something like the day before the deadline, or was it several days before the deadline? It was just, I wasn't very happy. I'd been waiting for this opportunity for years and years, and I was going to mess it up and my application wasn't ready. And then the email came through saying, postponed. And I remember being in my kitchen when the email arrived and I was like, yay! So that was the one time where it being postponed I was happy about, but everybody else was very disappointed. But yes, it's wonderful. It's finally gone.
Kids don't listen to this. This is not as advised.
No, certainly not. The second time round, I took it very seriously and I worked all summer on it. So yeah, lesson learned, I think. I think you have to take these things seriously. The competition is immense, and I was on the committee for selecting proposals as well. And you reject very, very good proposals just because it's very competitive. So yeah.
Thank you for giving us an insight to the kind of what you're doing up at the university. It was quite fascinating, the bits that I could understand.
Yeah, I hope you could follow.
I wanted to ask about the pristine gases.
Yes.
So are you finding that as you go further back, do you find that they're running out effectively, because as they get formed into stars and then the stars
so that's what's happening today in the current universe. That's right. So when you look back in time, you're looking at a younger universe.
So there's more of the pristine
so there's
gas.
more of the pristine gas.
But as it's, yes, I suppose, yeah, true.
And so we are running out. So actually, yes, so you see that you're able to trace the cosmic star formation rate. So we can see how much star formation is going on in the galaxies today. And then we can look a bit further back and we can see how much star formation, and we can do it by looking at all the galaxies, adding it all up, making corrections for the ones we don't see. And we can build up a picture of how much star formation rate, or how much star formation, sorry, there was at any time in the past. And what we find is that if we have a plot with redshift over here, where this is today and this is in the past, we find that star formation in the past, it went up because stars were forming, the conditions were right. But then it kind of, when the universe was about half its current age, it kind of reaches its peak. It stays at its peak for quite a while, and then it's been going down ever since, and we're down here now. And this is an indication of the fact that we're running out of this fuel, of this pristine gas. That's right, it's being used up.
Making more and more gold.
Well, maybe we're making more and more gold. That's right.
So
yeah.
Eventually
Eventually, you can continue kind of going in that direction. That's right. We'll run out. I mean, yeah, I think that is possibly true. Eventually, we see. So galaxies, we divide them into two types. We talk about star-forming galaxies and passive galaxies. Passive galaxies are also called red and dead galaxies. So these are galaxies that have somehow, again, another term, been quenched. Somehow their star formation has shut off. So if we just consider the simple model of pristine gas falling in, we should just be able to carry on making stars. Falls in, produces stars, the stars explode, more gas is released, more stars form, and this kind of carries on. But something happens which stops this star formation cycle. And we think what it is we think it's got something to do with these outflows. So probably the energy injected by these supermassive black holes at the centers of galaxies, which are also growing with time, they are injecting a lot of energy into the galaxy, which is just kind of throwing all the gas out. And for some reason, that gas does not fall back down. It stays hot. The gas has to cool down to kind of rain down. And that kills the galaxy. And the star formation stops. And so we're seeing that that's what's happening now. So it's a combination of, are we running out of the fuel that's coming in of this pristine gas, and possibly the conditions are not right now for that gas to actually fall into the center of the galaxy. So if we have these energetic outflows that they're keeping that gas away from falling in, that could also be happening and playing a role. Yeah.
Two obvious questions then.
Okay, the obvious ones are the ones that I'm most terrified about.
I'm assuming our own galaxy is not red and dead.
That's right, yes.
But if you did have a red and dead,
yes,
because obviously your galaxies collide, would merging galaxies potentially reignite activity?
Yes, there is evidence to suggest when galaxies merge that indeed that then can, through the merging of the galaxies, you can get conditions that allow gas to cool. That's the key ingredient. If the gas can then cool, it can then collapse. If it collapses, it can form stars. You then once again have a star-forming galaxy. But that's what happens with a merger, is that it allows somehow with the compression that occurs with tidal forces, the gas can then condense and cool. And so yes, we do see evidence for that. But that's becoming rarer. So we don't have a lot of information about mergers and the rate of mergers. That's quite tricky. When do you consider a merger, for example, is a really difficult question to answer. But there is evidence that, again, when the universe was at the peak of its star formation rate, there were more mergers. And so the universe is constantly expanding. And so we're becoming increasingly separated from other galaxies. So any mergers that could have happened, well, a lot of them have already happened, kind of thing. So even that's kind of slowing down. Yeah.
When you were talking about the spectra, getting the spectra from these, and you said that you took out the elements that were in our own galaxy, you can do that. But how easy is it to take out? Because it's difficult to know what's between our galaxy and what you're looking at. And how, you know, could a lot of that be something in there that we don't really know about and can't see in other ways, but that is actually interfering with the spectra that you're getting?
So that's the beauty of spectra. It does allow us to remove all this stuff very nicely. And the reason is because these transitions, these chemical transitions, when oxygen 3 at wavelength 5007 or whatever absorbs a photon, it can only ever happen at that wavelength, right? So this is just the chemistry behind the absorption. These different elements, they absorb photons at very particular wavelengths, if that makes sense.
Yeah.
So if there is some gas in the host galaxy and it absorbs a photon at a particular wavelength, and the element that's absorbed that photon, let's say it corresponds to silicon. Silicon is one that we see very frequently. We will see that happen at a particular wavelength in our spectrum. Yeah. And so we know that that must have happened. If it's happened at that wavelength, it must have happened. Okay, let me just go back. Does redshifting make sense? Yes. Should I? Yeah. So you understand how if the absorption happened at the GRB host galaxy, yes, the wavelength at which that happened has been redshifted. Does that make sense? Yeah. That's quite, I probably should have had a slide about that, because that is a little bit, that is quite complicated. Yeah. So if we have, so for example, well, I talked about the hydrogen and when we see hydrogen. So hydrogen, that big absorption trough happens at 1215 angstroms. So an angstrom is 10 to the minus 10 meters. So it just happens at this particular wavelength, right? 1215 angstroms at redshift 2 actually corresponds to 5,000 and something angstroms, right? Or 4,500 angstroms, something like that. Because it happened at 1215 then, yes, and then that light traveled and stretched. Yeah. And so when we see it, that line has shifted. Yeah. If there was hydrogen then in some intervening galaxy, we'd see it in a different place. And if it was within our galaxy, we'd see it at 1215. Yeah. Now we can't see 1215. We haven't got spectrographs from the ground that cover that wavelength range. That's UV, and UV light thankfully doesn't get through to us. But that's why our GRB spectra, if we want to measure metallicities, we need that hydrogen. We can only do it if they're far away, otherwise we miss it. It's not covered by our spectrograph. But that's why with spectra, it's incredibly precise at removing these contaminants, if you like.
Thank you.
Yeah. Pleasure.
Sorry, another one. You mentioned several times the oxygen.
Yes.
Is that just a satisfying thing to know you've got the degree of accuracy that you need to make the measurement, or is it signifying something else?
It's just got to do with the fact that it's a very nice luminous line. It's really what it comes down to. So oxygen, in terms of emission, I mean, that's not quite true. In terms of emission line diagnostics, the most reliable ones have oxygen in there. So these diagnostics reduce down to some fairly simple equation, which is going to say something like the log of that line divided by that line multiplied by 0.35 plus 8.2. That's kind of what it reduces to. So you just need to measure those lines and stick them into the equation. And oxygen is a key one there. And the reason why oxygen is key is because, well, it's nice and luminous, which means that we can see it easily. And so people on purpose produce these diagnostics that include that line. But oxygen is the most abundant metal in terms of mass that there is in the universe, and it also emits really easily. So if it gets excited, it emits really brightly. So that's why we like using oxygen. But I think I was pointing out the oxygen really just because there's the fact there's a doublet. That's another key thing. So because there's two of them, if there's only one line, how do I know whether that's oxygen 3 at redshift 3 or hydrogen at redshift 1? But if it's two lines, I can say, that's the oxygen doublet. So that's the other thing why it's a nice line.
Other questions we've got? Anything from online? Are you still out there? I was going to ask, sort of, because bringing those gaps together between the QSOs, is there anything that modelling can do to help you rather than pure experimentation, or are there just so many variables that you wouldn't know how to model? Yeah,
that's a really good question. So I really want to use models, but we don't really have the models yet. So there are two principal kinds of models that are useful for this kind of thing. One of them is these things that are called cosmological hydrodynamical simulations. So they are very sophisticated, enormous simulations that take many years to run on these supercomputers. And they provide beautiful data, and the images really look like galaxies. But what happens there is, because they reproduce such large volumes of the universe, they have to sacrifice something. What they sacrifice is resolution. So they don't really get down to the nitty-gritty detail, which is very important when you're doing this kind of analysis, because our pencil beams that look at GRBs and our pencil beams that look at QSOs are really just crossing a very small portion. I mean, in the Z direction, they're crossing a really big part of the galaxy. They're crossing the whole thing. But in terms of the spatial kind of projected on the sky. And so we need that high spatial resolution. Then if you look at the simulations that look at exquisite detail and high resolution, they look at single galaxies. And so I think they can provide some insight, but you're always going to have the argument of, but you've only simulated 5 types of galaxies, and how does that change if your galaxy is smaller or higher star forming or whatever. So we can use both, and I definitely want to try to guide us a little bit, because we do have degeneracies, we do have discrepancies, and models should be able to help us. But I think there's work to be done on both sides, to be honest. Yeah.
What's the rate of GRB discoveries at the moment then? Because you didn't seem to have too many dots on that.
No, so the difficulty is, so GRBs we get about a couple a week, but that's the prompt emission. Frankly, I don't care about the prompt emission. I want the afterglow, and not only do I want the afterglow, I want a high resolution spectrum of the afterglow. And so that little by little, you're crossing out your original kind of decent samples, because to get a decent spectrum of a GRB, you need to be there on day 1. So if that night you can't observe it with your spectrograph because it was cloudy, or because your program didn't take priority, then you don't get it. So actually building the sample is quite a slow process. It's just all about the time, it's about how quickly. If we had a spectrograph in space, a high resolution spectrograph in space, which wouldn't be affected by clouds, then maybe we'll get somewhere. So yeah, gotta wait for that.
Yeah. So in terms of your 10, what's the prospect for the next group? Is it another 10? Is it 100?
Definitely not 100. No, I mean, I think I could easily propose. So you saw, in terms of how many GRBs do we have with very accurate absorption line metallicities, we're approaching 60, 70. But, and I would love to put in, maybe I should just go for it. I would love to put in a proposal to JWST to try to get them all, with some kind of justification to say, I believe we'll get at least 70%. But it's just not going to, the politics, that's not going to work, because the amount of time that I will be requesting would be on the order of 200 hours or something, and JWST. So it's a balancing act. So I think I'd be happy to double it. That's fine, I'm not overly ambitious at the moment. Yeah, slow progress.
Any other questions? No? Well, I'm still intrigued by the JWST because after seeing Dr Becky Smethurst on Christmas Day,
oh yes,
she's trying to cook Christmas dinner.
Yes.
I work in a world where sort of I kind of can make a plan and it's going to happen next week. But you live in a world where you make your plans and it's years.
Oh, well, so that's true for the people involved in actually building JWST. And I don't have that kind of patience. So I admire those people enormously. And not only are they dedicating their entire career to building these things, then they have to sit there and watch it launch. And I was nervous watching it launch, but I can't imagine the people that actually have their instruments on board, how nervous they must have been. And there are so many disaster stories, you know, it's still very risky business. For the likes of me, we're waiting for it. It's kind of in our calendar, but astronomers are terrible with deadlines. So by and large, we kind of put everything in order in terms of where's the deadlines, which means everything, we're doing it 3 days before the deadline. I mean, JWST, like I said, I took it more seriously this time round, but by and large, we're quite bad at kind of pushing everything right up until the end. Yeah, so very different kettle of fish. We just look forward to when JWST will launch. Yeah.
So is there another generation of telescopes that's actually going to assist in all your work, or is JWST going to be sort of the last flagship for your career, or you imagine there's going to be something bigger and better or different?
I think eventually there will be. For now, this was, I think this is probably one of kind of the peaks for me. I am also very interested in the X-ray emission. That probes something different. So similar idea, GRBs have X-ray afterglows. And so you can use the X-ray and the absorption in the X-ray to look at something else. And there was a mission called Athena, which apparently is still due to be launched in the 1930s, which was going to provide me with beautiful X-ray spectra. That far surpassed anything we have now. And so I was very much looking forward to that. But unfortunately, there are money issues. And so the European Space Agency has said, yeah, sorry, Athena, you're going to have to downsize. And downsizing means getting rid of that beautiful high resolution spectrograph. So that was something that was on my list of things to look forward to. But for now, I think I'm going to, yeah, I personally, there will be something else, but I don't know what that is at the moment. Yeah.
So, okay.
Well, thank you very much.
Thank you very much, Patricia. Excellent talk. I hope everyone was equally bamboozled as you whizzed through, and then I managed to grab a bit of reality back in there and understand. But part of it is the fascination that you're studying something that's just so far away and trying to piece it together to try and work out how our early universe actually worked. Yeah. Because we just don't know, do we?
No. Well, I mean, we know quite a lot. It's amazing how much we do know, actually. Yeah. But yeah, there's still plenty to find out. Yeah.
The toughest of the sciences, because all you can do is look, you can't touch.
Yes, that's right. Yeah. We can't control our experiments. And I think a colleague of mine once complained about somebody, I think we were in a physics department. And so you've got lots of physicists doing real things, you know, solving real problems. And so sometimes as astrophysicists, we were like, you know, what was the point of what we're doing? And I think she got asked that question a little bit along the lines of what's the point? And she was seeing error bars. We really understand our uncertainties because we can't control our laboratory. It means that we need to really understand, yeah, the data as it's coming through. Yeah.
Excellent. So thanks everyone. We'll see you, or if you're into astrophotography, we'll see you in a week's time for Lee Pullen's talk. It's back here. So that's the 8th. And then you're going to enjoy the Christmas social. If you didn't know about it, blame Prim because she's been organising it. That's really cool of me. No, it's been going around the WhatsApp group. There's been a few notes about it, about getting in touch. So hopefully everyone has seen that. We've got 19 people, is it? And that's at the Architect on the 12th. Monday, is it Monday the 12th? Yes. Monday the 12th. So hope to see everyone there. And we'll be organising loads more, not just outreach, because we've been quite outreach heavy, but more for the members as well, observing evenings, the like. So not only have we got Mitch as our 16-inch Dobsonian go-to, which is like, wow, I like free. That's got big telescopes and free, but we also got the Prof now, which is the 8-inch telescope. The owners have asked, or the ex-owners have asked us to call it the Prof. So we're going to call it the Prof. And so that's an 8-inch go-to.
downstairs.
And we've got the unistellar EV scope downstairs, which belongs to the museum as well. So in terms of, if you don't know how to use telescopes, you've got no excuse now, because we've got loads of props around. All you have to do is say, can you show me how to use that? Can you show me how to use that? So tomorrow there's a session on the EV scope. That's for the museum and that's for a few outreach people. But what we'll do is probably extend that out to other people if they want to know how to use the unistellar EV scope, because it's part of the resources of the museum now. And as Bath astronomers, we get to use those resources as long as we're trained up. And so this will be part of that. So tomorrow's is full, but let us know. So if there is demand, no, it's in the evening. Yeah, but if there is demand for doing another one, then we'll organise another one. And hopefully, if it's clear tomorrow, they'll actually get out there to do some observing. And some people, mad people, like Jonathan at the back here, there's a big list called the Herschel 400. And Jonathan has set himself the target of using this new telescope downstairs to try and record as many of the first, and for the benefit of the museum. So just to have the imagery there, that's a huge challenge. People take 10 years doing it. Yeah.
If I'm not on holiday, that's fine.
Yeah. So as you know from Chris, we're in a really good position at the moment. We've got lots of great relationships with Bath Preservation Trust, the Abbey, whole school homeschooling groups all around. We've got schools, we've got Cubs and Scouts, guides asking it. So effectively, if you want to get involved, just attend more sessions, you can, as informally as you like. But this is part of your society, and it's bubbling with energy. So if you want to get into it, or just be on the sides, whatever you want to do, it's up to you. Okay, but thank you very much for coming on. Thank you for being in the AGM. Thank you very much, Patricia, for guiding us through GRBs and mechanicity, which everyone knows, and there will be a question in the Christmas quiz.
There's a quiz coming up.